Hi everyone, we're going to give it a few more minutes for more people to start watching the live stream, and then we'll go ahead and get started talking about mixtures and aqueous chemistry today. All right, for those of you that just joined, we're going to give it a few more minutes until more people are on the live stream. But go ahead and also make sure that you have joined the Zoom breakout rooms, just because that's really helpful for practice problems. There will be some pretty long ones today. Okay, great. So we're going to go ahead and get started. So if anyone, all the slides are on B-Courses, so sometimes it's easier to take notes. So there's a PDF available online. Feel free to download it as we go through. That can be helpful to write out answers to practice problems. All right, so today we're going to talk about mixtures and then also start talking about aqueous chemistry. So first off, let's quickly discuss what the difference between a mixture and a compound is. So a mixture is a combination of substances that are mixed together And a mixture can have a varied composition. This means that you can have mixtures that are different from one another. And the formation of a mixture requires a physical change. For example, some types of mixtures are sand, which is a mixture of a bunch of different kinds of particles, but they're all just kind of physically mixed together. Or you could have granite. So if you look at like a granite countertop, you can see all the different specks inside of it. And those are all different substances that have been mixed together. And then you also have air, which is all around us, which is all made up of mostly nitrogen and oxygen, and then a lot of other gases too. On the other hand, we have a compound. So a compound is a combination of elements that have a fixed composition. And the formation of a compound requires a chemical change. So when we talked earlier about bonds, that's really important in defining a compound, because compounds all have a chemical change, and that means that all of these elements are bound together. So for example, if you consider water or salt, these are all types of compounds. So let's quickly go over the differences between mixtures and compounds. So for a mixture, you can separate the different components using physical techniques. Because they're not bound together, you can use a lot of different techniques to separate them. And the compositions are also variable. This means that you can have different types of mixtures that have different compositions. And properties are related to, the property of the mixture is related to the properties of the individual components. On the other hand, you have a compound. So components in a compound cannot be separated by using physical techniques. Again, think of salt or sodium chloride. It can be hard to separate the sodium from the chloride. And the composition is fixed. For example, you'd only have one sodium and one chloride. And the properties are unlike those of its individual element components. Once these elements are bound together, their properties do significantly change. So again, feel free to post in the live chat if you have any questions, but otherwise we're going to go ahead and move on. So let's discuss types of mixtures. So you can have a heterogeneous mixture, which is a mixture in which the components are not uniformly distributed. For example, granite is a heterogeneous mixture of different minerals. If you look at this picture here, you can see how like the black and the gray specks and the white specks are not evenly distributed throughout the material. So because of that, this would be a heterogeneous mixture. On the other hand, we have a homogeneous mixture. In a homogeneous mixture, all of the components are uniformly distributed. So if you look at this picture of syrup, we know that syrup is a homogeneous mixture of sugar and water. So when you mix them together, you get this sort of solution where visually to our eyes, we cannot distinguish any of the components. So now let's discuss solutions. So a solution is another word for a homogeneous mixture. For example, seawater is a solution of salt and water. By definition, the component that's present in the larger amount is called the solvent, while the component that's present in the smaller amount is called the solute. So that can be more easily visualized if we look at this diagram here, where you have the solvent. In this case, that's the large blue area, and then you have all of the small orange dots, and that's the solute. So because we have less orange dots than we have of the big blue, the orange is the solute, and then the blue is the solvent. And together, they make up a solution. There are two broad categories of solutions. One is aqueous solutions. So by definition, these are solutions in which the solvent is water. And then we can also have non-aqueous solutions. So in these solutions, the solvent is not water. So a good measure of how much solute we have in a given solution is concentration. So we can define the molar concentration as the amount of moles of solute in a given volume of solution. So you'll also hear the word molarity referring to concentration. So molarity is actually another word for molar concentration, but they mean the exact same thing. So by definition, molarity, or molar concentration, is the amount of solute in moles divided by the total volume of solution in liters. And we can define units for molarity as molar, and we can denote that using a capital M. So the molar unit is defined as moles per liter. So definitely make sure that you have the right units when you do this. For example, you wouldn't want moles per milliliter, you would want moles per liter. So again, remember dimensional analysis, because that can be really helpful here as a good check that you have the correct units. So let's briefly go through an example calculation together. For example, you have 0.029 moles of sugar that are dissolved in a 0.2 liter solution. So just quickly on paper, in about 2 minutes, try to calculate this, and then we'll go through the answer. And again, during this time, if you have any questions from this slide or any of the previous ones, please feel free to post it in the live chat. Does anyone need more time? Okay, great. So we'll go ahead and go over this example. So to calculate the concentration, you would divide 0.029 moles by 0.2 liters, and that would give you 0.15 moles per liter. And by convention, we would write this in units of molar, so then that would be 0.15 molar, which is represented by the capital M. Okay, great. So that is all of the basic definitions of different kinds of mixtures. So now we're going to specifically look at aqueous chemistry. So all of these solutions we're going to talk about have water as their solvent, and they're all homogeneous mixtures, so water mixed with other things. So I'm going to give you guys another minute in case you have any questions, and if not, we're going to move on to aqueous chemistry. Okay, great. So let's move on. So first, let's talk about solubility. So a soluble substance is one that dissolves in a specified solvent. So for example, if you have sodium chloride, you can mix that with water and it would dissolve and you would get a solution. So in this picture here, I have a similar example where you have water, which is your solvent, and then you have sugar, which is your solute. And when you mix that together, you fully dissolve the sugar in the water and you get a solution. So this would be a soluble substance because all of the sugar was able to dissolve in the water. On the other hand, you can have an insoluble substance. So this is a substance that does not significantly dissolve in water. So by definition, a substance is insoluble if no more than 0.1 moles per liter will dissolve in the solvent. So basically, we have the definition just because sometimes you can have a small amount of your substance dissolve, but mostly it's all still insoluble. So for example, if you look at this pictures of sand and water, you have the sand and the water separate, and when you mix them together, you still just have a bunch of sand underneath all of your water. So this is an example of an insoluble substance, because no matter what you're going to do, the sand will never dissolve in the solvent, and you'll always have these two layers. Versus our previous example with the sugar in the water, you would get that nice clear solution because the sugar had completely dissolved in the water. So next we can talk about electrolytes. So an electrolyte is a substance that is present as ions in solution. And electrolytes are called electrolytes because they actually can conduct electricity through the charged ions in solution. So for example, in our sodium chloride solution, that sodium chloride, once it's in water, actually exists just as sodium cations and chloride anions once it's in solution. So here we can visually show that by distinguishing the anion from the cation. So you would visualize this as a separate sodium cation and then a separate chloride anion that are not together in solution. They are surrounded by other water molecules. And then that means it's dissolved, and so then you would call it an electrolyte. On the other hand, you can have a non-electrolyte. So this is a substance that does not form ions in solution. So for example, if you have sugar molecules, those will dissolve in solution, but they don't separate into different ions. So here we have water surrounding each of the large sugar molecules, but they're still all neutral molecules, right? There are no ions that form. And because there are no ions that form, we call it a non-electrolyte. So within the class of electrolytes, we can define two more categories. So one is a strong electrolyte. This is a substance that is present almost entirely as ions in solution. On the other hand, you can have a weak electrolyte. So this is a substance in which most of the molecules remain intact, but there are some ions. So sort of the intermediate case between a non-electrolyte and an electrolyte. So I'll give you guys a minute in case there's any questions about these definitions. Please post it in the chat. Understanding these will be really important moving forward with some of the reactions we're going to do in the next few slides.
Please make sure to accept your breakout room invites if you haven't. If you're not in a breakout room, go double check. Like maybe the invite is hidden behind your Zoom window or something.
Okay, great. So I think I gave enough time to account for the lag, but again, feel free to post in the live chat and we'll go back and answer your questions. So moving on, let's talk about precipitation reactions. So sometimes when we mix two electrolyte solutions, an insoluble precipitate will form. This is called a precipitation reaction. By convention, we use AQ in parentheses to indicate which substances are dissolved in water or aqueous species. And again, like we discussed earlier, these species, if they are electrolytes, which they are for this, in this case, will exist as ions in solution. And then you would use S to indicate the solid that has precipitated. So right here, I've written out a reaction of silver nitrate and sodium chloride that reacts to form silver chloride and sodium nitride. So here I've denoted which species exist in solution and which species precipitates. So in this case, sodium chloride precipitates out of solution when we react these two electrolytes together. And that is denoted by having the phase, the solid phase, in the parentheses after the molecule. And we will discuss how to determine when a precipitation reaction occurs later in class. Okay. So we can also write out a complete ionic equation for a precipitation reaction. So the complete ionic equation shows all the species as they actually exist in solution. So since the dissolved aqueous species actually exist as ions in solution, we write each ion separately. So for example, if we take the reaction we had on the last slide with the silver nitrate and the sodium chloride, we would want to rewrite that as individual ions. So your silver nitrate would exist as a silver cation and a nitrate anion. So you would write those as their separate charged species. And your sodium chloride would be the same. So you would also write that as your sodium cation and your chloride anion. And then on the product side, we know that we react to form silver chloride. So since that is a solid, it cannot be dissolved in solution, right? Since it is the solid that is precipitating out of the reaction. So that in that case, we would still write silver chloride and denote that it's a solid. But our sodium nitrate in the aqueous solution, we would break that down and we would write a sodium cation and a nitrate anion. So then that would be referred to as the complete ionic equation because we very explicitly wrote all of the different species present in the solution. But then, as you notice, there are some species that appear on both the reactants and product side. So then what you can do is cancel those out of the reaction. So in this case, we see that the nitrate anion is both a product and a reactant, so you can cancel them out. And then their sodium cations are also both on the product and reactant side. So these ions are referred to as spectator ions. They're ions that do not actually participate in the reaction, but they're still present in the solution. So when we write the net ionic equation, what we do is we remove all of these spectator ions from our reaction equation. This is just to make things easier to write. So then we would just have the species that actually react. So in this case, that would be the silver and the chloride ions, and they react to form the silver chloride solid precipitate. So again, in the complete ionic equation, you would write down all species as they actually exist in solution. So you would write down all of the individual anions and cations in your aqueous solutions. And then when you write your net ionic equation, what you would do is you would remove the anions and cations that do not actually react. And then that simplifies it, so then you would just simply write the anions and cations and then the solid precipitate that is formed by that reaction. Okay. So now, in your groups, please go ahead and work on these 3 examples. So first, as always, we want to always balance the reaction. So as your first step, please write the balanced overall reaction for each of these 3 reactions. Then write the complete ionic equation, and then simplify your complete ionic equation to write your net ionic equation. So I'll give you guys around 5 to 10 minutes for this, and feel free while you're doing this example to post in the live chat and I can answer any questions. But go ahead and work in your breakout rooms. Okay, so I'll give you guys about 2 more minutes, but please let us know if you think you'll need more time than that. And again, feel free to also post any questions in the live chat and we can answer them. Okay, great. Does anyone need more time for this example? Okay, great. So we're gonna go ahead and go over this. But if you still need more time, it's not too late, post in the live chat and then we can wait a bit longer. I know this is a lot of questions at once. Okay, so first we'd want to write the overall balanced reaction. So in A, that reaction is actually already balanced. So you would just need to write the same thing. And then to write the complete ionic equation, we would separate all of the aqueous compounds into their individual ions. So that would be the silver nitrate, the potassium chloride, and the potassium nitrate. You would not separate the silver chloride because that's a solid. So that will not exist as ions on solution because it's an insoluble solid that cannot be dissolved. So then when we write out the complete ionic equation, we include everything. We include all of these species. And you would want to be careful to make sure that you have all of your charges and that you also write AQ after all of the aqueous species to denote that they're ions in solution. And then some of these cations and anions don't actually participate in the reaction. So in this case, you see that before the reaction, you have these nitrate anions, and these potassium cations. And after the reaction, you still have potassium cations and nitrate anions in solution. So they aren't actually reacting, right? They are the same before the reaction as they are after the reaction. So for that reason, they're called spectator ions, and you would just cancel them out when you write the net ionic reaction. So in this case, our net ionic reaction would be silver cations plus chloride anions, which goes to the silver chloride solid. So moving on to question B. So in this case, the reaction I gave you isn't balanced. So you would need to go ahead and balance it. And when you do that, you find that you need the stoichiometric coefficient of 2 in front of the sodium nitrate on the product side. So once you add that 2, then your reaction is all balanced. And then once it's balanced, you can go ahead and write the complete ionic and net ionic equations. So just like we did for part A, we would write all of the individual ions for all of the aqueous species. So you would have the magnesium cations in aqueous solution plus 2 nitrate anions. Again, there's 2 of them, and we know that because we were given magnesium and 2 nitrate anions in the original problem. So you want to make sure that you keep track of all of the different coefficients here. And then you would have 2 sodium cations plus your carbonate anion. And that would go towards your insoluble species plus, again, your sodium cations and your nitrate anions. So in this case, you can see that you have 2 nitrate ions and 2 sodium ions that are on both sides of the equation. So again, that means that they're not really contributing to the reaction. They just kind of exist there in solution. So those are your spectator anions. So you would just cancel them out from both sides, and then you can write your net ionic equation, which is your magnesium cation plus your carbonate anion going to your magnesium carbonate solid. So for the last one, I guess I corrected the typo in the answer but forgot in the question. So it's the strontium bromide, not boron, and you would again need to balance this equation. So in this case, to balance it, you would need 2 stoichiometric coefficient in front of your potassium bromide. And just like the others, we would expand all of the aqueous components into their individual ions. Okay, so someone just asked, how do you determine the charges of the elements? So like we talked a few lectures ago, you can get that from the periodic table, or you can get that from looking it up in a table. So for all of the carbonates and nitrates, those are something that's all tabulated. So you can look that up, but you should be able to predict it just from knowing the charge of the magnesium or the sodium. So again, we don't expect you to have memorized all of the charges of all of the different elements, but we expect you to know where to go to find that information. So in this case, you could go to the periodic table, or you could look up a table of different charged compounds. Okay, so someone asked, can you just look at the solid that is made in the product side and just separate its atoms in the reactant side, or can you miss something from not separating everything individually? So that's a great point. And then once you get practice with this, many of you will probably be able to anticipate the net ionic equation just from looking at the original equation. So that is okay to do. But right now we want you to go through the steps of first writing the balanced overall reaction, then the complete ionic reaction, and then your net ionic reaction. So I think that, once you have a lot of practice, that's something that you can easily do just from scratch. Okay, so someone asked, so we split all of the aqueous compounds into writing out the complete ionic equation. Yes, exactly. You would want to write that as the individual ions, so the cation and the anion. Okay, so I'll keep going through example C, but great questions, keep posting in the chat. So then for this example, you would write out all the ionic species. Okay, So someone asked in problem B, where did I get the 2 for Na plus? So if you look back at the original question, so here, let me go back in the slide. So we have two sodium like molecules, and then the carbonate, right? So we know that there's 2 sodiums for every 1 carbonate, just because that's given in that molecular formula that is in solution. And we want to keep track of how many of each elements we have. So we know that we will always need 2 sodium cations for 1 carbonate anion. Again, that's just because that's given to us in the molecular formula that was in the original reaction. So that's why when then you go to write the complete ionic equation, you have to put a 2 in front of the sodium. That's because you still have to have 2 sodium cations for every 1 carbonate anion. Hopefully that makes a bit more sense. Basically, you want to separate all of the different aqueous species, but still keep track of the numbers of each, and that can be helpful. Would it have been wrong to have put in the complete ionic equation for B, Na with a 2 plus charge instead of 2 Na with 1 positive charge? Yes, that would have been wrong because sodium is one of the cations that will always have a +1 charge. So if that's confusing, I would go and look at the lecture slides, particularly from last class, and then some from last week too, where we discussed that. Even if you didn't know that, you know that the charge of the sodium has to be given by that molecular compound. So because it's Na2 and then carbonate, we know that we have to have, we know that carbonate has a charge of 2 minus because we can look that up in a table. So that means that your sodium, each of your 2 sodiums has to have a charge of +1. So that would kind of have to rule out that your sodium had a +2 charge. Yeah, but that's a great question. So if anyone is still confused about how to determine charges on elements, definitely see us after class in the Zoom room and we can go over that more. That is really, really important, and we hope that from talking about oxidation numbers and things like that, that's a bit more clear. But it is hard to always know exactly what the charge of every species is. I have to still look up a lot of these sometimes or go to a periodic table to check. So as long as you know where to go to find that information, you should be okay, but you just need to know how to find it. That's the important part. Okay, great. So just to finish out part C, your complete ionic equation would be written out like this. And then for your net ionic equation, you would cancel out all the species that are not involved in the reaction whatsoever. So that would be your 2 bromide anions, and then also your potassium cations, and that would give you the net ionic equation. So I'm gonna pause for like another minute in case there's still more questions. Continue posting in the chat and we'll try to get those answered before moving on. What if there is no solid on the product side? So we're actually about to discuss that soon. So if there's no solid on the product side, you would still write out all of the individual anions and cations in solution. And then if you have the same thing on the reactant side as you do on the product side, that means no reaction has occurred, right? Because it's exactly the same. So then you wouldn't have a net ionic equation. But great question. We will discuss how to determine if reactions actually occur in the next few slides. Okay, great. So if there's no more questions, we're going to go ahead and move on. So there's something called solubility rules. So these precipitation reactions are driven by the formation of an insoluble compound. So like someone in the chat mentioned, sometimes you can mix two electrolytes together and you'll not get a precipitate, right? You'll still just have two electrolytes mixed together. So in that case, there is no precipitation reaction. That's because a precipitation reaction is specifically referring to reactions in which you mix two electrolytes together and a solid actually forms, right? So you can't have a precipitation reaction in which you mix two solutions together and then after your reaction you still just have the same two solutions. That's not a reaction. So because of that, we need to understand when an insoluble compound will actually form, because that will allow us to predict if these precipitation reactions will actually occur. So to do that, we can use solubility rules. So the solubility rules will allow us to determine if an insoluble compound will actually form in the first place. So again, these are a lot of rules. At least when I was in like high school and college, we were never expected to memorize this. A table was always given to us. So hopefully in Chem 1A, they are also kind to you. But we'll just go through some examples. But our goal here is for you to, again, basically know that the solubility rule table exists and where to find it and how to use it. But not to necessarily memorize all of these details, but to really understand the concepts here. So don't get bogged down in the details. Again, we're just focusing on how to use it. But we're not going to try to memorize all of the different solubility rules. Okay, so let's go through a few examples. So we think about sodium chloride and water. We may ask ourselves, is sodium chloride in water soluble or insoluble? So to answer that, we would go to the solubility table, and then you see on one of the entries on the table, it says that under soluble compounds, it says chlorides, bromides, and iodides, except those that have silver, mercury, or lead salts, those are always soluble. So if they're on the left-hand side of the table, that means they're always soluble. So because having a chloride anion and the sodium cation, according to these rules, would then mean that it has to be soluble. So that would lead us to believe that sodium chloride is soluble. But suppose you had silver chloride. So again, if you looked at the same rule, at first you may think, oh, it has a chloride anion in it, it should be soluble. But then if you get to the very end of this rule, it has those exceptions. So it says chlorides are soluble except those that have a silver cation or the mercury and lead cations. So then that means that our silver chloride is actually insoluble. So let's go through one more example. So say we have sodium phosphate. So we can read through this table again, and then on entry under the insoluble side. So again, all of the entries under the insoluble heading mean that if you have these things, your compound will be insoluble. So this rule says that carbonates, chromates, oxalates, and phosphates are insoluble, except for those of group 1 elements and the ammonium cation. So sodium is a group 1 element. Again, this is something that you would know by looking at a periodic table, but at this point we don't expect you to know the groups of all of the different elements. So because sodium is a group 1 element, that means that this is actually a soluble compound. But then if we consider calcium phosphate, calcium is not a group 1 element, but then you still have the phosphate, so that means that it is insoluble. So I'll give you like a minute to digest that before we go on to doing some practice examples in our breakout rooms. But again, I just want to emphasize our goal here is for you to understand how to use this table. And it can be pretty confusing because with every single rule there are exceptions, but just try to keep track of it. It can be confusing. Okay, so just to summarize before we move on to an example, so we can look up a solubility table, and what that does is it provides all of the different rules for how to determine if a compound will be soluble when it's in water. This is specifically for electrolytes, so it's for water. And in these tables, they separate the rules into two different categories. So on the left, you have rules that determine if something will be soluble. So if it falls under the category on the left side of the table, that means your compound will be soluble. And then on the right-hand side, we have all of the insoluble compounds. So if your compound falls under one of these rules, then that means that it is insoluble. Okay, great. So again, don't worry about memorizing this. The chart is, at least in my experience, always provided, but that is definitely up to your Chem 1A teacher to decide. Okay, so now let's do some practice with solubility rules. So are the following compounds soluble or insoluble in an aqueous solution? So take 2 or 3 minutes in your group and go through and try to determine if these are soluble or insoluble. I have the tables shown here. There are also tables available online, but again, feel free to refer to this one for class. And again, also post in the chat if you have questions too. Okay, so someone asked if it's insoluble, then would that mean that it's the precipitation product? So yeah, then that means that this compound is not soluble in water, so it would be a solid. So that does mean that it would be the precipitation product. We'll discuss more about these reactions on once we go over this example, but yes, that's a great point. Does anyone need more time? If not, we'll go ahead and go over the solutions. Okay, great. So let's go ahead and go over the answers. Again, feel free to post questions in the chat. So for the first one, we have magnesium chloride. So if we look at this table, we can see that there's an entry for chlorides underneath the soluble column. And this entry says chlorides, bromides, and iodides are soluble, except those that have the silver, the mercury, and the lead salt. So since we have a magnesium salt, we know that this rule applies to us. So that means that magnesium chloride is soluble in solution. So for the second one, we have lead sulfate. So we can, again, find the entry under this table. So the one highlighted in blue at the bottom says sulfates are soluble, except those of calcium, strontium, barium, lead, mercury, or silver cations. So since we have a lead cation, that means that our compound will be insoluble, right? Because lead is one of those exceptions to this rule. And then in our third example, we had calcium sulfide. So if we go over to the right-hand side of this table, we see an entry that describes what to do if there's a sulfide in your compound. So this rule says that sulfides are insoluble except those of the group 1 and group 2 elements. So calcium is a group 2 element, so that means that this is actually a soluble compound. Again, that's because calcium is one of the exceptions to this rule. So I'll give you guys a few minutes to ask any questions in the chat, and then we'll move on to talk about how this actually affects precipitation reactions. Okay, great. There's no questions at all in the chat. So it looks like everyone's doing great with learning how to use the solubility table. So let's go ahead and move on. Okay. So we can also use the solubility rules to predict reactions. So we know that precipitation reactions will only occur if an insoluble product can form. So we can use the solubility rules to predict if mixing two electrolytes will result in a precipitation reaction. So for example, we have this potential reaction where we have potassium chromate and we have silver nitrate, and we have these in solution. So then we can ask ourselves, will a reaction actually form? Will a reaction actually happen? So we know that we can use the solubility rules to determine this. So we'd want to ask ourselves, are any of the possible products insoluble? So first off, what are the possible products? So we know that the reaction would have to occur, so we can't get the same thing we already had. So that means we can't have a potassium chromate solid or a silver. We can't have a potassium chromate solid because we already know from our reaction that it is soluble. So we know that we need to think about if potassium nitrate is soluble or not. So we can go ahead to this table and we can look it up, and we see that under the solubility column there's an entry that says compounds of group 1 elements are soluble. So that means that your potassium nitrate is soluble. And so our second possible product of this reaction would be silver chromate. So we can also go through and look for this in the solubility table. So at the bottom we have an entry that says sulfates except, I think I highlighted the wrong one. So it's on the other side, sorry, that's a typo. So the chromates, carbonates, chromates, oxalates, and phosphates are insoluble except those of group 1 elements. and ammonium. So that means that because we have a chromate anion, that compound is actually insoluble. So because we were able to predict that one of our products is insoluble, we know that this precipitation reaction will actually occur. So then we can write out that reaction. So we know that we'll have our potassium nitrate, and because that's soluble, we can label that as aqueous by denoting that with the AQ after the one product. And then we'll also have our silver chromate, and because of the solubility rules, we know that that is a solid. Okay, so someone asked, how do we know what the possible products are? So that's a great question. So we know that for a reaction to actually happen, we can't have the same thing that we started with. So that means we can't have potassium chromate. And since there's only two possible cations and two possible anions, we know that they basically have to flip spots. So that means that instead of having potassium chromate, we must have potassium nitrate, simply because that's the only other option. It can get more complicated if you have more than two electrolytes, but for now we're just going to think about this simplest case. So hopefully that makes more sense. Basically, it's just because to have a reaction, you can't have the same thing you started with. So that means that you just need to flip the anions and cations to figure out what the possible products are. You could also figure that out by going through and trying to figure out if potassium chromate or silver nitrate are soluble. We know from what we were given in the question that those are soluble because that was denoted with the AQ after the compound. Does that make more sense? Great. Awesome. Okay. So then, because of this, we know that a reaction occurs because we actually had a solid precipitate occur. And that was all we had for lecture today. So tomorrow we'll continue with a bit of aqueous chemistry, and then starting next week we'll switch over to talking about waves and other materials that can help prepare you for Chem 1A. So please continue to ask any questions in the chat, and we'll stay on the live stream for another minute. But then otherwise we'll go ahead and close the Zoom breakout rooms, and then you can ask any questions in the Zoom room afterwards.